that, is there any question? Is there any question regarding yesterday? Okay, good. So let me put this a bit better. Okay. Okay, so yesterday, one of the heuristic arguments that we gave for the absence of global symmetries was based on black holes, right? Like we said that if we have a global symmetry, then we cannot distinguish the black hole from very far away, and this is going to violate some entropy bound. And this is the metric that I gave you. This is the ansatz for the black hole, and for a Schwarzschild black hole that is neutral, the point was that the number of states grows with the entropy, and since the entropy, the horizon, does not depend on the global charge, this sum is infinite. Okay, so you sum over all possible charges, this goes to infinity. Now, how this is, then I promise you that this is solved if the global symmetry is gauged. Okay, so how is this solved? Well, if I consider now a Reissner-Nordstrom black hole, so that is charged under a gauge charge, then what happens is that the metric is sensitive to this gauge charge. Okay, so this would be the typical horizon metric, such that R minus is 2 times the m, where m is the mass of the black hole, and R plus is a G square, Q square, G Newton. Okay, this is G Newton. So the black hole now depends not only on the mass, but also on this gauge charge. Okay, this electric charge. And this also implies that there is an extremality bound, in the sense that for a given charge, there is a minimum mass the black hole can have, because otherwise you have a naked singularity. Okay, so this is the extremality bound. So all black holes must satisfy that their mass is bigger than their charge in order to have a smooth horizon. Okay, to avoid some naked singularity which is not hidden by the horizon. So if we now do the same game and count how many remnants do we have, how many states below some energy scale, then we again have to sum over the charge, but now the charge is upper bounded, cannot go to infinity. Okay, so here it was going to infinity, right? But now the charge goes, if I am summing up to some energy scale, so black holes of mass m smaller than e, then the charge has to be smaller than this, and if you sum this, taking into account that the entropy, right, is just equal to the charge in these solutions, then you get that the result is 1 over g. Which means that as long as the gauge coupling is different from 0, you get only a finite number of states. Okay, so this is how is it solved if the symmetry is gauge. Now, of course, you could say, okay, here I can already see that if g is very small, I might still get a problem. Maybe it's not infinite, but if g is very small, if the gauge coupling is very small, I can still have a parametrically large number of black hole states of remnants that would violate entropy bounds. So this is still problematic if g goes to 0, and of course this makes sense because in the limit in which the gauge coupling goes to 0, you restore a global symmetry. So this is breaking down in a continuous way. Okay, any question about this? Okay, so gauging the symmetry is good, it solves the problem, but it can still be problematic if the gauge coupling is too small. Okay, this is kind of the conclusion. So what do we do then? Okay, how quantum gravity gets rid of this issue? Well, one possibility is that these black holes, I mean, these states that I'm counting, I'm assuming that they are stable states, like you just count over all of them, so they all count for the entropy. But if they are unstable, then they will not count as different species. So one possible way out is that the extreme black holes are actually unstable. Okay? And this is precisely what the weak gravity conjecture guarantees. Okay, so the weak gravity conjecture is the statement that can be motivated by the statement that black holes must be able to decay so that they are unstable. And this is possible whenever in my theory there is a particle such that allows this kinematic decay. Black holes can decay. So if I have, imagine that we start with some black hole, which is extremal, so the charge is equal to the mass. Now this black hole can decay, we can think that, let's think if it can decay to other two black holes. So the first, a black hole must satisfy this extremality bound. So the charge must be smaller than the mass, okay? Otherwise we have an singularity. But if one of the decay products satisfy this, the other one must satisfy the opposite, just by charge conservation. So it's going to be super extremal. So it's going to have an singularity, meaning that this cannot be a black hole. And the only option is that this is actually a particle. I mean, a particle can have any charge, right? Like there is no constraint on that. There is no horizon. So in order to allow an extremal black hole to decay, I must have some particle with a charge bigger than the mass. And this is the weak gravity conjecture. So this decay mode is going to be just the Swinger effect that one can compute. And as an exercise, if you want to do it, you can derive what I just told you with words. Like just using energy conservation so that the mass, the initial mass is bigger or equal than the sum of the masses, no? The two decay products, and charge conservation so that the charge is equal to the sum of the individual charges of the endpoints. One can show that the charge to mass ratio of the original extremal black hole that I'm just putting to 1 is smaller than the charge to mass ratio of the particle to which the black hole decays to. Okay, and this is the gravity conjecture. That is a particle with a charge to mass ratio bigger than the charge to mass ratio of an extremal black hole. Any question? Okay, so let's write the definition properly. It's a very important conjecture. So the point is that given a gauge theory weakly coupled to Einstein gravity, there must exist an electrically charged state with a charge to mass ratio which is bigger than the charge to mass ratio of an extremal black hole in that theory. And this is going to be some order 1 number that one has to fix depending on the theory and the black hole solutions. And of course, this is in Planck units, okay? The mass is given in Planck units. And also take into account that this charge is the quantized charge times the gauge coupling, okay? So it's the physical charge of the state. This is the gauge coupling. This is the quantized charge. So for example, if we have Reissner-Nostrom black holes, meaning that we just have an Einstein-Maxwell theory and usual charge black hole solutions, then this order 1 number, so the charge to mass ratio of an extremal black hole It just depends on the dimension of the space-time. Okay, just to make it sharp. So it's not just a random order one number, it's the order one number which corresponds to the extremality bound of the black hole. Okay, so why is this called weak gravity conjecture? Since now it's coming from black hole physics. Well, because if I have some particle whose charge to mass ratio is bigger than some order one number, this also implies that gravity acts quicker than the gauge force over this particle. In fact, you can check if you take the Newton force, the gravitational force, and impose that is smaller or equal than the gauge, the Coulomb force, the gauge force, and you put all the order one numbers and all the factors here, then you get precisely that the charge to mass ratio of the particle must be bigger than d minus 3 over d minus 2. So it's exactly the same order one factor. The one can derive both from extremality bound of the black holes or from imposing a no force condition, so that the gravitational force is bigger than the gauge force. So you can do also, if you want, you can do this as an exercise. Check this.
Sorry, isn't
Yes.
isn't extremal black holes supposed to be stable?
No, so the point is that because of the existence of this particle that has a charge to mass ratio bigger than the charge to mass ratio of the extremal black hole, then the black hole is not going to be, extremal black hole is not going to be stable anymore. It can decay through Swinger effect. It can emit these charge states. So you get rid of the charge and you lose the mass. Okay, this is the particle.
So
if you don't have particles, it's stable. But if you have the particles in your theory, it's unstable.
So what happens in supersymmetric theories when you embed this solution in there?
Okay, good. Yes. So in supersymmetric theories, talking about decay, then it's like the extreme case. What happens in the supersymmetric theory is that this is saturated. So it's not bigger or equal. What happens is that BP states will saturate the weak gravity conjecture, so that it, like, the charge to mass ratio is equal to the charge to mass ratio of the extremal BPS black hole. And then it's not really a decay, but a fragmentation. Then the statement is that an extremal BPS black hole, of course, it's stable because it's supersymmetric, but can fragmentate. I mean, it can fragmentate into smaller BPS states. Okay.
Yeah.
So that's the statement, okay? Without supersymmetry, it's really a decay, a physical decay. With supersymmetry, it's a fragmentation into smaller pieces that are also BPS. Okay. Good. So here I explain it for a particle and for a usual gauge field. But the point is that this is valid for any P-form gauge field in your theory. Okay, so I think yesterday, probably if you didn't know, you learned about higher force symmetries, which appear when you have some P-form gauge field. So in those cases, if you have a P-form gauge field, then again, you must have an electrically charged P-1 brane, satisfying that the charge to mass, charge to tension, okay, now the tension is going to be equivalent to the mass in Planck units, is bigger than, again, like some order one number, which is given by the charge to tension of the extremal black brane in the theory, okay? Extremal black brane. And in the case, again, of like Reisner-Nordstrom black brane, so if I just have Einstein plus a P-form gauge field, then this order one number is P times D minus P minus 2 over D minus 2. okay, where D is the dimension of space-time and P is the degree of the gauge field. So for example, if I have, let's write here, so let's put gauge field, and what is the state that the gravity predicts. So here I have 0 form, 1 form, 2 form, 3 form, and so on. So this is an axion. This is a usual gauge field. This is a B field, a 2-fold gauge field, then a 3-fold gauge field. And for each of them, what happens? I mean, this is the typical case that I need to have a particle. For a B field, then the state which is electrically charged is a string, right? For a 3-fold gauge field, the state that is electrically charged is a membrane. So in 4 dimensions, this is going to be a domain wall. And for a 0-fold gauge field, I mean an axion, okay, let's see, this is an axion, then the state which is electrically charged is an instanton. And I think I will explain it, or otherwise Lars will explain it. That's why the weak gravity conjecture can have interesting implications for inflation. Okay, because it also constrains the action of the instanton in combination with the gauge field of the action, which is the decay constant. And you see that as why like Transplanckian actions are problematic in the same way that a tiny gauge coupling is problematic. So this will be for the future. I think Lars will explain this. If he doesn't, then I will do it another day. Okay, any question? Okay, so let me just.
I had a question.
Yes.
regarding your previous transparency.
Okay, fine.
And
yes.
With regard to previous, yes. Does your convention for normalization of Q or M differ from the standard one? Because in the standard notation, the extremality condition is Q equal to M, at least for D equal to 4. It is D Q equal to M, but your relation is.
Yeah, when I put Q equals M, it was a different, I was putting this order 1 factor to 1, like without caring about the order 1 numbers. The convention in which you get this D minus 3 over D minus 2 is, let me write it here, is when I take that the Lagrangian, I think it's the typical one. I have M Planck square over 2 R minus 1 over 2 G square F square. Yes.
So, for example, for D equal to 4, your relation becomes Q over M equal to 2 1/2, not equal to 1.
Exactly. Actually, sorry, this is a square root.
It is not a standard relation.
It's a. I mean, it just depends on the normalizations here. So if you have heard that this 1 is because this 1 over 2 is different. The usual one that we always use in the Swampland and also in string compactifications, and I think it's also a standard one for black holes for at least part of the community, is that you have this 1/2 here for the Einstein term, and then exactly in 4 dimensions, this is 1 over 2, and sorry, here I think I missed a square root, because I remember this is square root of 2. Let me just double check quickly. Yes. Yeah, so this is actually the square root of this, sorry. Yeah, so here there's also square root. Yes. So the charge, exactly, the charge summary is the square root of D minus per D minus 2. So it becomes 1 over the square root of 2 in Einstein mass square. For a field canonically normalized in this way. Of course, it's just a matter of convention. You just have to be careful about what is the definition of the charge that you are using.
Okay.
Yeah, so typically one just have some order one number and you can normalize it with respect to that number. And then you just say that it's one, but there is some number that depends on the dimension. And it's the square root of 2 in 4 dimensions. Okay, so yeah, okay, here there was sorry, not the square root because I put the square, the charge to mass ratio square here. Okay, otherwise there is a square root as well. Okay, and here I was just writing that the Gibbs coupling for a zero form for the action is 1 over the decay constant. That's why a large decay constant is problematic because it's like a very tiny Gibbs coupling. Any other question?
Yes.
Yes.
I was wondering if that existence condition include composite objects like you know, like brains forming higher dimensional brains in the presence of flux, or any composite particle, zero dimensional particles, or it needs to be elementary ones.
Okay, very good. So here, I mean, at this moment, I just told you that you need to have some state, but I didn't specify the nature of the state. Like, what is, for example, the quantized charge of the state? So what you're asking is also equivalent to say that when you have the physical charge is the quantized charge times the Gibbs coupling, and how large is this quantized charge?
Mm-hmm.
Is the elementary particles, or the quantized charge is of order 1, or it can be very large, so we are even talking about some small black hole.
Mm-hmm.
This is something which in the original definition of the weak gravity conjecture is not specified. The motivation coming from black holes is not strong enough to be able to answer that question. But we will see that from the perspective of string theory, what we observe is something much stronger than just having one state, but really what we get are towers of states, so even including elementary particles. So that the first one, like the state with the minimal charge that satisfies the gravity, actually has a very small charge, and it's not composite. But for that, we will need to go to string theory. I mean, just black holes is not enough to motivate that. More questions? Okay, so just one further comment. Here I was just talking about having Maxwell and gravity, like just some gauge field. But the extremality bound is something that depends on your theory. I mean, this order 1 factor can depend, and for example, it changes if you have massless scalar fields. Okay, so with massless scalar fields, this extremality, let me call it gamma, this order 1 factor, okay, gamma. This charge to mass ratio of the extremal black hole, it's going to depend, can depend on the massless scalar fields. So for example, if I just have a theorem in which the gauge coupling is parameterized by some scalars, like in dilaton, Einstein-Maxwell dilaton theory, so that the gauge coupling depends exponentially on some scalar field, then this gamma, this order 1 factor we are talking about, becomes alpha square 2 plus bd minus p minus 2 per d minus 2. Okay? So this is the contribution coming from gravity, but there is an additional contribution coming from the scalar fields in your theory, and how the gauge coupling is parameterized by the scalar fields. So this is, I wanted to point out this because notice that in the presence of scalars, with scalars, the extremality condition, the super extremality, let me call it like the good gravity as a super extremality condition, because the particle must have a charge to mass ratio bigger than the extremal value. Okay, so super extremality is no longer equal to a repulsive force condition. So before we said that this extremality condition was equivalent to say that gravity acts weaker than the gauge force. But in the presence of scalars, now I have a new force, which is given by the scalar. So what I have is that the gauge plus the scalar, I mean, there is a third force in the game. So you could try to impose also a repulsive force condition, which is the same than before, no? Like in the end, the gauge force is repulsive and the gravitational force is attractive. You can think that the weak gravity is sort of a repulsive force condition, so that the particles of the same charge, they will repel each other. And this, in the presence of scalars, gets modified to this triple balance of forces, but this is no longer equivalent to the superextremality condition in general. Okay, so if I compute this gamma from the extremal solution, and I compute this order one number, this gamma, from imposing this repulsive force condition, I can get a different result. So then the question is, okay, what is the correct definition? Now I have two options. I can think either of black holes, or I can think of balance of forces. This is an open question in research. Sometimes we typically distinguish this and call this repulsive force condition, while this one we still call it weak gravity conjecture, that is bounded to the black holes. And I mean, like all the string theory examples we know satisfy both of them, even if they are a bit different, but there is no counterexample to any of the two. It's just that the order one factor changes, but still both satisfied. And still, the difference between the two becomes completely relevant if we are at weak coupling. Okay, so at weak coupling, there has been several works showing that the difference disappears. Okay, so that when the gauge coupling goes to zero, it becomes small. Then the same particle, which if I have some particle satisfying the weak gravity conjecture, then it will also be satisfy this repulsive force condition automatically. Okay, so the difference is only important if we are kind of in the middle of the model space, like strong coupling regimes and so on. Okay, if we are with coupling, that's the difference disappear. But it's important to keep it in mind. Okay, any question?
By the way, this is the weak Einstein gravity conjecture, right? So by gravity, you mean Einstein gravity.
Yeah, so far it's Einstein gravity. Now, you can ask to what extent this could be valid beyond Einstein gravity. In that case, all the motivation from black holes disappears because this is different if we don't have Einstein gravity. But you can study this from the CFT perspective, like for example in ADS CFT, and consider CFTs that are dual to ADS, which is not Einstein gravity. And in many cases, I mean, it's still an open question, but it seems it's still satisfied. So maybe the point is that, I mean, this is just a motivation, how everything started, but now it's going much like far beyond this. And it seems that there might be some general feature of quantum gravity that is also present when you study the CFTs, that still make this weak gravity conjecture to hold, regardless of this motivation of black holes. But then we need to discover what that is.
I wonder if we had another dating degree of freedom for gravity, like scalar metric theory, how we add this force to this inequality to the left or to the right. So I believe we must go to the Einstein frame first, right?
Yes, exactly. Yeah, this only makes sense if you think of Einstein frame. Otherwise, I don't know how to define it. It can be a bit, go both ways. I agree. So actually, like the way, just as a comment, for example, Ramparti and Aharoni, they formulated this on this repulsive force condition on the CFTs in terms of the dimension of the conformal operators. And what the translation is that you have some convexity of the charge operators. So that this inequality gets translated to some convexity of all these these conformal dimensions that one can aim to check. So that would be like a way to prove this statement. Okay,
Excuse me.
yes.
How this weak gravity conjecture can be reconciled with the cosmic censorship and existence of naked singularity?
Yes.
Are they consistent?
Yes. So exactly. So it's very linked to with cosmic censorship in the sense that you need to have these particles to avoid some naked singularity. But even beyond that, like there has been some works by Horowitz and Santos and others showing that there are, let me put it here, I want to write some relation to with cosmic censorship. They have shown that there were some counterexamples to with cosmic censorship in which the gauge field apparently can grow without bound and generate some net singularity in the end. And these counterexamples disappears precisely if there is a particle that is friendly with gravity conjecture. So there is indeed a very nice correlation between the two things. So at least in examples, it has been shown by Horowitz, Santos, and others that you need to have very with gravity to avoid a violation of weak cosmic censorship. Okay, more questions?
Excuse me. May I ask?
Yes.
Okay. Okay. Can we interpret this this slide that it's as if the gauge coupling depends on the massless scalar fields, or from the form of the Lagrangian?
Again, can we? So if the gauge coupling depends on the massless scalars, like in this case, then what?
Yeah, I mean, is this the same thing? I mean, is this? Yeah, I mean, did I interpret it correctly? That
yes. So exactly. So the point is that this extremality factor, like the Charles-Truman ratio of the extremal black hole, which is this order one number that we need to check, can depend if you have massless scalars, because the gauge coupling then is can be parameterized by this massless scalar. So whenever the gauge coupling is parameterized by some scalar field, this scalar field is going to include some contribution to your extremality bound.
Yes. Thank you.
Yes. Here I give an example with this dependence. This is the gauge coupling. This dependence is exponential, which is what happens in all the weak coupling points as far as we know. But like in general, when it doesn't matter the function, like if the gauge coupling depends on the scalar, this is going to modify the extremality bound. And you have to, depending on the case, you have to compute it and check what it is.
Yes, thank you.
More questions? Okay, so this conjecture, I mean, okay, what I told you now is this motive is coming from black holes. Then we will see during the lectures, and also, so maybe you see in other lectures that there are many more. I mean, I will show you that there are many more evidence, many more motivations beyond this. This is kind of the original one, and one which I think is important and it's also playing a central role in recent years is the connection with global symmetries. So we already said that this is already, like the presence of this state, it's sort of a censorship, like it's given an obstruction to restore a global symmetry. Okay, so if we have the gauge coupling goes to zero, it might be parameterized by some scalars, then this is a limit in which one restores a U1 global symmetry. And therefore, something must go wrong. What goes wrong is that you have new states, such that the cutoff of your theory depends, set by the mass of these new states, behaves at least, it can be smaller, but at least is going to behave as the gauge coupling. Okay, so that when the gauge coupling goes to zero, the cutoff of the EFT also goes to zero. Now, right now, as we said, like the weak gravity conjecture just tells you that you must have just one state. I mean, that's enough for allowing black holes to decay. But what we observe in string theory and what it's motivated by the absence of global symmetries is that it's not just one state, but we get infinitely many states. So the EFT really breaks down. It's a drastic breakdown given by quantum gravity that you cannot fix by adding one more state to your theory. Okay, if you just had one state, you can just integrate it in and have a new EFT that is valid and it's going to restore a global symmetry. So the way in which this works is that you get, as the gauge coupling goes to zero, you get more and more states satisfying the gravity conjecture. So in the end, you get like an infinite tower of states whose mass goes to zero when the gauge coupling goes to zero. Okay, and this connects with the distance conjecture that I will explain now. Okay, so what's the connection? Well, if I'm thinking of string theory or quantum gravity theory, all the parameters, the expectation is that there are no free parameters. In the sense that all parameters are determined dynamically. They can be understood or parameterized by some scalar fields. So changing the parameters is like changing the vacuum expectation value of your scalar fields. So it's like moving in the modular space or field space of my theory. Okay, so imagine that we have the parameter space, like different values of the gauge coupling, for example, like different EFTs with different gauge couplings. It's equivalent to a field space in string theory, in the sense that when I move in this field space, I can change the value of the scalar. For example, I can send some scalar to infinity and approach one of these boundaries. And this is going to make some gauge coupling go to zero. Okay, so moving the field space is like moving in this parameter space. And then the limit in which the gauge coupling goes to zero, as I already wrote here, necessarily is going to be pushed to infinite distance in this field space. Because the point is that I cannot have global symmetries in string theory. So I cannot restore a global symmetry at a regular point of the field space. So this is pushed to boundaries, to infinite distance. Okay, so G goes to zero happens at phi goes to infinity, like at the infinite distance boundaries of the modular space. So no global symmetries in the middle. Okay. Okay. Okay, so global symmetries can only be restored at infinite distance in the field space. Good. So what is happening now? Well, what is happening is that indeed, as I will give you many string theory examples, but what happens in all the examples in string theory is that indeed, like when we take a limit in which we move to one of these infinite distance boundaries of the modular space, in which there might be some gauge coupling that goes to zero, the cutoff of the EFT also goes to zero in a continuous way. Okay, so this is the cutoff. And it's dictated by the presence, so EFT breaks down when approaching some infinite distance limit, because there is an infinite tower of states that become massless. So they become light. And the cutoff of this tower, is given by the mass of the tower, which behaves, as we said, as the gauge coupling, according to the weak gravity conjecture, but also in terms of the field distance, it behaves exponentially. Okay, and this is what the distance conjecture is what I will explain now. Okay, so the statement, just to recap, as I approach an infinite distance boundary of the modular space where I might restore a global symmetry, the cutoff of the EFT must go to zero in a continuous way, because I get infinitely many states that are becoming light, and the mass of these states behaves with the gauge coupling, as the weak gravity conjecture says, or we'll see that it behaves exponentially in terms of the field distance that I travel which is what the distance conjecture explains. Okay, good. So let's define then this exponential behavior. Okay, so the point is that the distance conjecture tells you, yeah, how the mass of the states behave as you approach an infinite distance limit without talking about the gauge coupling, just in terms of the distance you travel. So let's read the definition carefully. Yeah, the point is that if I have some EFT weakly coupled to Einstein gravity, and I have some field space, I have some scalars, right? So let's think, for example, have some Lagrangian theory. And I have some scalar fields. And this is the field metric, okay? So I'm gonna have some field space. If they are massless, it's a modular space. And this is the metric in this modular space. Then the statement is that there is an infinite tower of states that become exponentially light at any infinite distance. Let's put any infinite field distance limit. Okay, so that if I have, let's put like, let's draw again our modular space. If I am at some point P and I move towards a point Q that is near one of these boundaries, the point is that the mass evaluated at Q must behave exponentially in comparison to the mass evaluated at P. Must behave exponentially in terms of the geodesic distance that you travel in this field space. And this must happen whenever you approach one of these infinite distance boundaries. So whenever you can make this field distance parametrically large, okay? Okay, so this is the conjecture, okay? So the conjecture is whenever you approach some infinite distance limit in the modular space, whenever you take a limit, you get new states becoming light. They become light exponentially in terms of the geodesic distance that you travel in the modular space. Where this lambda is again like some order 1 constant that again is not, is not specified by the conjecture, but in recent years we have been able to understand what it is. And it's related to the nature of the tower. It's related to whether in this infinite distance limit, you are going to decompactify or get new strings or what's going to happen. Okay, so we will see this more carefully. And of course, since I get infinitely many states, I cannot keep an Einstein gravity description anymore. Okay, you cannot have infinitely many states weakly coupled to Einstein gravity. So the EFT drastically breaks down. Okay, I cannot just integrate the states in and get a QFT. So the EFT breaks down. Okay, with a cutoff that depends on the mass of these states. Any question?
May I ask a question?
Yes.
So is it part of the conjecture that there always exists a point at infinite distance, or are there?
Okay, very good.
That we know it does not exist?
Yeah, very good. So in the original paper of, I should have said this distance conjecture is from Oguri and Baffa. The weak gravity conjecture was from Arkani Hamed, Baffa, Lugos, and in the original paper of Oguri and Baffa, they also conjecture that there is always an infinite distance point in the modular space, so it's kind of part of the conjecture. But I think this is kind of a outdated version. Like I think recently what we have seen is that, I mean, if we are in flat space, if it's really like a flat Minkowski space, there is no counterexample to this, like there is always some infinite distance limit. But for example, in ADS-CFT, I have counterexamples. So in ADS-CFT, you can, the modular space of the ADS gets mapped to the conformal manifold of the CFT, the manifold of the marginal operators. And then, for example, in 3 dimensions or smaller, there are compact conformal manifolds. So there are no infinite distance limits in those cases. So I don't think it's true that there is always an infinite distance limit. Still, all the counterexamples are only in ADS. So maybe there is a difference between Minkowski and ADS in that sense, which actually might be related to not having scale separation and other things that I can explain if you wish, but that's like a more present developments.
Okay, thank you.
Excuse me.
Question? Yes.
I was somewhat confused about how the volume in the field space is related to the number of states in this
The volume.
statement.
So this is just about the distance, okay, not the volume. The distance is infinite, so you have a non-compact space, but still it could be that the volume is finite. And this is what happens actually in the string theory compactifications, because what you get asymptotically is some hyperbolic metric, some hyperbolic space. So that the hyperbolic spaces are non-compact, but still have finite volume. So you can, because the curvature is negative, it's a negative constant curvature. So you can have infinite many states becoming light in a non-compact direction and still keep a finite volume of the modular space. Okay.
Oh, is it related to the number of states? My question is that the distance, you say the distance, okay. How is it related to the number of states? You're saying there is an infinite tower of states that become exponentially light, yes?
Yes.
So you are counting the number of states. How is it related to the distance? I don't understand.
There is a relation. They say that if you go to infinite distance, if you go to infinite distance, then you should have infinitely many massless states there. If you are approaching the infinite distance limit, then they are becoming light, no? So now you could say, okay, why infinitely many and not just a finite number of them? And the point is that the conjecture is this, but the reason, the intuition is that the effective field theory must drastically break down. You cannot have, because this is a limit in which you are restoring probably some global symmetry. So you cannot have just a finite number of new things, because if you just have a finite number of things, you can just integrate them in and have a new QFT that is coupled to gravity and is completely fine. So this is really what you get is an infinite number of new things, because then the EFT drastically breaks down and you cannot have QFT anymore. Like there is no local effective field theory completely breaks down. There is no way to have a local effective field theory description anymore. And that's the way in which quantum gravity avoids to restore this global symmetry, regardless of the description of the theory. And of course, you can think that you have like parametrically large numbers and you have some infinite tower, but it's only in the limit in which you get to infinite distance that you really count that there are infinitely many, because then they all are massless. Otherwise, they have a mass which goes parametrically high in energies, right? It's like a tower of states. So you start with some M0 that behaves exponentially, and then you get n M0, like 2 M0, 3 M0, and so on. So they all become massless in the limit only. Is it clear?
Thank you.
Good. Okay, so this is interesting because if the EFT, as we said, breaks down, if the cutoff behaves in this way, this is also giving us an upper bound on the field range that an EFT can describe. So let me write it here. So the point is that since the cutoff behaves in this way, delta phi cannot be bigger than 1 over lambda log m plum over the cutoff. Okay, so for if you have an EFT that you want to be valid up to some energy scale, then there is a maximum field range that you can describe within this effective field theory. And that's why I will explain probably tomorrow, this can give constraints on inflation, for example, where you need a large variation of the scalar fields. Okay, but it's important to remark that it's a correlation. Okay, so what quantum gravity is giving us is a relation between the cutoff in energies and the cutoff in the field space, which are two things that in quantum field theory are not connected, but in quantum gravity they become connected. Okay, so I think it's already 54. So let me just do one thing. Let me just make 2 comments and then we will stop for today. So first, just to recap, these 2 conjectures are examples in which EFT expectations can fail in the presence of gravity. Okay, so what we are saying is that gravity and the Swampland distance conjecture are telling us is that the cutoff of the effective field theory can be much below than the Planck scale. So the quantum gravity cutoff can be below the Planck scale if you have small gauge couplings or large field distances. Okay, so this is smaller than m Planck if you have small gauge couplings or large backing expectation values. Okay, so this is one of the most important messages of the Swampland. It really plays a central role in many of the other Swampland ideas, like if all the other Swampland conjectures you might hear about, they are somehow related to this. Okay, they are somehow related, they are consequences on different corners of having these new states that arise when the gauge couplings are small or the field distances are large. So this really plays a very central role on the Swampland program. And it's something which is surprising from an EFT perspective, because in quantum field theory it's completely fine to have a small gauge coupling, right? Like we even like it, like we have perturbative control and we can compute things. But quantum gravity is telling us, well, be careful, because if it's too small, you get an approximate global symmetry, and that doesn't make sense in quantum gravity. So you cannot have small gauge couplings. So it's really like EFT expectations are failing in that sense. But from a string theory perspective, and this is what we will discuss tomorrow, it's very natural. Okay, so this is an example in which it's surprising from EFT, but very natural from string theory. So tomorrow what we will do is to study what is the nature of these states, how these states appear in string theory compactifications. Okay, so we will start with easier examples and then complicating the story a bit more, so that we can always identify these new towers of states. Okay, and they are very natural from the string theory perspective, because this is just, I mean, if you have learned about string theory, maybe you have learned about all the string dualities, like T duality, S duality, all these things. So the states that play their central role in all these dualities are precisely the states satisfying these conjectures. So understanding why these conjectures are true is like understanding what is behind dualities, like why we have all these different dual descriptions. So we'll see that we'll see examples from string theory, and we will see that typically they always signal either a decompactification limit. So we'll see that when the scalar field corresponds to some volume of an extra dimension, and you make the volume large, then you are going to get Kaluza-Klein towers becoming light, and this is a typical decompactification limit that satisfies both conjectures. And also we'll have string perturbative limits, in which you get towers of string modes becoming light. Okay, so this is the task for tomorrow. Understand this in string theory and understand what are the possibilities, what is the nature of the states, and try to provide evidence for this. Okay, so the whole point is that this was just bottom-up argument based on black holes and global symmetries, but from string theory you can derive sharp and rigorous tests in which the presence of the towers is translated to some mathematical statements about the geometry of the compactifications that you can then prove. Okay, so with this, I will finish for today, and let's see if there are.
Thanks, Irene, for a great talk. Are there questions?